So now that we have looked at the very simple two-level system which can exist in the energy levels 0 and epsilon, let's look at something a little bit more complicated. It is still a two-level system, but it's clearly it has an experimental relevance. What we want to look at is a magnetic system of spins. And this we have discussed earlier also. So the spins can be either in an up or a down state, and there are n such spins, right? Now this magnetic system has a magnetization m, right? So if there are n1 spins which are in the up state and n2 spins which are in down state, correct? Further, we also have to look at this condition where my total magnetization is given. So essentially what I'm trying to find out is S as a function of m comma n, and for these I have to figure out the configurations which are possible m comma n, not just n but given a value of magnetization, and the magnetization m is n1 minus n2, number of up spins minus number of down spins, and n is n1 plus n2. So this actually simplifies our life. One can use these two equations to write down n1 is n1 plus m by 2 and n2 is n by 2 1 minus small m. Where I have defined the small m, this is now no longer an extensive quantity, but this is a magnetization per spin. Now it's purely a combinatorics. If I want to find out S as a function of omega, S as a function of m comma n, I calculate the total number of microstates, and that number of microstates is given by n1 factorial, n2 factorial, right? Which would mean that this is going to be n factorial, n1 factorial, n minus n1 factorial, correct? So now we'll keep it as n2 because we have already derived an expression for n2. Omega comma n is now it's a long algebraic process. So this we will write down as n factorial, n into 1 plus m by 2 factorial, n into 1 minus m by 2 factorial. So this is ln n factorial minus n into 1 plus this factorial minus ln n by 2 1 minus n factorial. We use Stallings approximation, which tells me that ln n factorial is n ln n minus n. So this becomes n ln n minus n, n by 2 1 plus m ln 1 plus n by 2 1 plus m minus n by 2 ln so ln n 1 minus m by 2 plus n by 2 ln, no, this is just going to be 1 minus m. So ln omega m comma n is equal to, again one has to go through all these elaborate things, but some of them are pretty easy to figure out, right? So you see this minus n is going to cancel out with plus n by 2 and plus n by 2 from here, right? So essentially you will have, and this is going to cancel out because they two have opposite signs. So you are going to have n ln n, n by 2, 1 plus m ln 1 plus m n by 2 minus n, 1 minus m, ln n by 2, 1 minus m, right? Good. So n ln n, n by 2, 1 plus m, ln 1 plus m by 2 minus, so we are expanding this part here, minus n by 2, 1 plus m, ln n, minus n by 2, 1 minus m, ln n by 2, minus n by 2, 1 minus n, ln 1 minus n by 2. Sorry, we will not include the 2 over here. This means that if I take this expression and if I take this expression, I'm going to get minus of n ln n. So n by 2, 1 plus, I'm left out with this nice little expression, minus n by 2, 1 minus m, ln 1 minus n by 2, right? So I can take n outside. This tells me it's 1 by 1 plus m by 2 plus 1 minus m, ln 1 minus m by 2. And therefore the entropy S comma m comma n is minus nkb 1 plus m by 2 ln 1 plus m by 2 plus 1 minus m by 2 ln 1 minus m by 2. From this, of course, one can calculate del S del m, and this is going to be H over T, the magnetic field. This is going to be one of the equation of states. Now clearly what we see over here is that this entropy has no energy over here, because when we started off we said that we have just n spins and these spins can flip without, so we did not even specify any interactions, so just that the spins can flip independent of each other. Now I want to specify that the flipping of the spins is dictated by the interactions. So let's say I write down that the energy is minus j sum over Si Sj, right? So this means that if the ith spin and this interaction I and j can happen only over the nearest neighbor. This angular bracket indicates nearest neighbor interaction. So which means that if I have a lattice, I have the ith spin, I have the I plus 1th, and I have the I minus 1. So if this spin is up, then it tries to flip this spin towards itself. The interactions are only between I and I plus 1 and I and I minus 1. Of course, this model in physics is a very simple model of magnetization and is called Ising model. We will not study it here, but we merely want to exploit this only in what is called mean field limit. Look, good. So let's say I have now, there is one more thing that one has to look at, is that this particular expression does not care about the dimension of the space, right? I have never said that this spins are sitting on a one-dimensional lattice. It can very well sit on a three-dimensional lattice. But this is pure entropy. Good. So this entropy is purely due to your configurations of the spins. Now I bring in the internal energy, right? So when I bring in the internal energy, I said, look, there is an interaction between the nearest neighbors, and if one is up, then the other one also tries to bring it to the same state. So if Si is in the up state, which means let's say it's plus 1, then if Sj is minus 1, in the down state, that means this energy is minus J. Sorry, it's plus J. On the other hand, if Sj is in the up state, then this energy becomes minus J, a more lower energy configuration. So this interaction itself tries to bring the spins in the nearest which are in the nearest neighbor in the same alignment. Good. So I want to solve this in the mean field limit, where basically I say that this sum I can replace as Si for Sj. So I want to evaluate this in the mean field limit. The mean field limit essentially means that I have a sum over I and j. So this interaction I replace by average of Si and average of Sj, and already I have defined that the magnetization per spin, which is essentially the average of Si, is small m. So I go to the ith site so that these two sum over I and j decouples, right? So I can write down this as minus j sum over Si. I go to the ith site, and clearly if I go to the sit in the ith site, this lattice point has a certain coordination number. Let's say if it's a square lattice, then this is the coordination number you're looking at. So these are the nearest neighbor points. It has 4, and we'll call this coordination number Z. So the ith spin is actually, if you is surrounded by Z number of spins, right? So therefore the sum over Z j gives me Z times n, and then I have minus j Z m. The sum over Si now is just n times m. However, now the problem here in this summation is that this you considered as the ith site, but in the next time you hop in over here, and this again you considered as the ith site. But the contribution of this site has already been considered over here. So there is a double counting which is involved. That is okay with us, except that we bring in a half factor, so that this becomes half j z n m square, right? So this is your energy. The free energy now. So now you clearly see that there are two competitions. One is from the entropy and the one is from the internal energy. So what is going to be the thermodynamic state of this? And that competition between these two is given by the minimization of the Helmholtz free energy, which is T minus S. And if you write down the free energy per spin, this becomes small e minus T times small s. The small e is minus half jz m square, which we immediately see over here. E over n is equal to small e is minus half jz n over m square, minus t times the small s, right? If so, well, one can write down this as half jz m square. We had the expression for the entropy over here, which we are going to use, minus, sorry, this becomes plus kBt one plus m by 2 ln 1 plus m by 2 plus 1 minus m by 2 ln 1 minus m by 2. This is the expression of the Helmholtz free energy per particle. If you are at sufficiently high temperature such that your magnetization is small enough, then I can expand this logarithm over here, and I can write down F as a function of temperature is a power series. A little algebra, if you expand this, this is going to give you plus kBt m square kBt over 12 m4 plus higher order terms, right? So this one I can easily write down as T minus Tc times m square plus kBt over 12 m4. plus higher order terms, right? If you now plot f as a function of temperature, then you clearly see that for temperatures greater than Tc, this coefficient is positive. So if I plot T greater than Tc, then of course I'm going to see something like this, f as a function of m comma t. If I plot, well, let's just write not m comma t, let's write f of If I plot t less than Tc, then you see that this coefficient has changed sign, and the functional form therefore changes. You develop two minimas at m naught, m minus m naught. This is what is called the paramagnetic state, and this is called a ferromagnetic state. A true ferromagnetism is very, very complicated, but it's a very simplistic coarse-grained modeling of the paramagnetic to a ferromagnetic transition. So you immediately see that this nice free energy explains your paramagnetic to a ferromagnetic transition, right? So this is the Landau Ginzburg free energy. We will not take this further, but just the fact that I wanted to illustrate that starting from this microscopic picture of the spins, we can derive not only the entropy, but even if we just consider the energy, the interaction energy in the mean field limit, we can actually come up with this very elegant description of a paramagnetic to a ferromagnetic state.